Michio Kaku and the Revolution in Cosmology, a universe that defies the textbooks. Dr. Michio Kaku, the renowned theoretical physicist and science communicator, is once again drawing attention by challenging some of the most fundamental assumptions of modern cosmology. A string of discoveries made by the James Webb Space Telescope (JWST), including the detection of mature massive galaxies that appear to have formed just a few 100 million years after the supposed beginning of the universe, has led Kaku and other forward-thinking researchers to argue that it is time to radically rethink our understanding of the cosmos. The discovery that shocked science. In mid-2023, the JWST captured its first deep-field image, an extraordinarily detailed look at some of the most distant galaxies ever observed. Scientists expected to see chaotic, primitive galaxies forming in the aftermath of the Big Bang. Instead, they were astonished to find several massive galaxies, some even comparable in size and structure to the Milky Way, existing at a time when, according to the traditional Big Bang model, the universe should have been too young for such complexity. This discovery poses a significant challenge to the current cosmological model, which holds that the universe began with the Big Bang 13.8 billion years ago and gradually evolved through stages of star formation, galaxy mergers, and expansion into the structured universe we see today. Kaku emphasized, there is no way that galaxies of that size and complexity could have formed within just a few 100 million years after the Big Bang. The data simply doesn't fit the theory anymore. A broken cosmology? For decades, students and scientists alike have been taught that the Big Bang marked the origin of the universe, and that everything we observe today emerged from a hot, dense state through a gradual process of expansion. Yet, according to Kaku, this is more of a working assumption than a proven truth. Many people mistakenly believe that the Big Bang theory is a proven fact, Kaku has said in interviews and writings. But in reality, it's a model, an interpretation of limited evidence, supported by mathematical extrapolations. The recent JWST findings bring this model into question, particularly because these ancient galaxies seem too large, too organized, and too mature for their age. The prevailing lambda-cold dark matter lambda CDM model, which combines Einstein's general relativity with the hypothesized effects of dark matter and dark energy, depends heavily on ideas that have never been directly observed. Dark matter and dark energy are inferred from indirect effects and mathematical necessity, not physical evidence. In fact, 95% of the universe, according to this model, is made up of these unproven entities. The Hubble tension and the problem of expansion. Another significant issue is the so-called Hubble tension. This refers to the fact that different methods of measuring the expansion rate of the universe, the Hubble constant, give conflicting results. Measurements based on observations of nearby supernovae suggest a faster rate of expansion than those derived from the cosmic microwave background, CMB. The JWST has confirmed this discrepancy, deepening the mystery and casting further doubt on the reliability of the current model. For Kaku, these inconsistencies highlight a deeper problem: the reluctance of the scientific community to let go of outdated assumptions. Science should be guided by data, not dogma, he warns. He believes that many researchers are clinging to the standard model, not because it continues to match the evidence, but because it's the only model they know how to work with. A universe of assumptions. Before the JWST, humanity had never directly observed the earliest galaxies or the so-called dark ages of the universe, the period between the Big Bang and the formation of the first stars. What scientists claimed to know about this period was based on simulations, indirect observations, and theoretical extrapolations. Now, with actual images from deep space, those theories are being put to the test, and, in many cases, failing. The JWST has revealed not chaotic proto-galaxies, but well-formed spiral and elliptical galaxies that appear far too soon in the timeline to be explained by the slow, collision-driven evolution posited by lambda CDM. If our own Milky Way took billions of years to reach its current state, how can similar structures exist at just 400 to 500 million years after the supposed beginning of time? Some cosmologists are scrambling to revise the model, proposing that matter might have formed much faster than previously believed. Yet this too seems like a desperate attempt to patch a sinking ship. The role of quantum physics and Kaku's vision. Michio Kaku approaches these questions not just as a cosmologist, but as a quantum physicist. Quantum theory, which governs the behavior of the smallest particles in the universe, has long stood in tension with general relativity, which describes the large-scale structure of space and time. Reconciling these two frameworks has been the holy grail of physics for over a century. Kaku is a leading proponent of string theory, which posits that the fundamental constituents of the universe are not particles, but vibrating strings existing in multiple dimensions, far more than the four we can perceive. While string theory has not yet produced verifiable predictions, it offers a conceptual bridge between the quantum and the cosmic. In Kaku's view, the failure of the Big Bang theory and the Lambda-CDM model to accommodate new data is not a crisis, but an opportunity. It invites us to explore new frameworks that better account for the complexity and strangeness of the universe. Science progresses through the collapse of its paradigms, he explains. The JWST is not destroying our understanding of the universe. It's giving us a clearer picture, and we must be humble enough to follow the evidence. On scientific humility. What distinguishes Kaku from many of his peers is his humility. Despite his fame as a best-selling author and media figure, he frequently reminds his audience that science is not about certainty, but about continuous questioning. Ignorance is not a weakness, he says. It's the frontier. He encourages both the public and the scientific community to embrace uncertainty as a sign of growth, not failure. We don't know how matter was created. We don't know the true age of the universe. And that's okay. These are the questions that keep us moving forward. Conclusion. Toward a new cosmology. Michio Kaku's challenge to conventional cosmology is not merely a critique, it's a call to action. The discoveries made by the JWST have unveiled a universe that is far older, more complex, and more mysterious than we ever imagined. They demand that we move beyond the comfort of established theories and seek out new models that integrate both the quantum and the cosmic. The age of simplistic narratives may be over. We are entering an era in which science must become more interdisciplinary, more open-minded, and more responsive to the surprises the universe has in store. After all, as Kaku reminds us, the universe is not only stranger than we imagine, it is stranger than we can imagine.